Hello everybody, so my name is David Brochart and I currently work at Quantstack, and this talk is about parallel processing using CRDTs. So first, what this talk is not about. It's not about embarrassingly parallel problems where data is nicely chunked into separate parts that different cores could work on, because there would be no conflict in this situation. Nor is it about fuzzy data where you can work on shared data, but you kind of merge them with some kind of mathematical means. For that, you would probably use a library like Dask. This talk is about mutating shared data concurrently, as it's typically the case in web servers or databases. That doesn't mean it doesn't apply to scientific computing, because you can, for example, deploy ML workloads with that. So let's let's talk about the basic ways we can parallelize code in Python. First, async await, but you probably know that with async await, nothing really happens in parallel. It's more like a time multiplex sequence of instructions, and we talk about concurrency rather than parallelism in this case. There is also multithreading in Python, but as you may know, there is the infamous GIL that prevents us to really run threads in parallel, unless you do that in C extensions, but you have to manage it yourself. Free-threaded mode is coming to Python 3.14, coming in 1 week. This is also called no-GIL, so that might change things, but you will still have to manage the complexity of locks, and many of us don't want to do that. There is also sub-interpreters that are coming to Python. They were introduced in Python 3.13, I guess. It's going to be improved in 3.14. They run in the same process, and thus they share the same memory space, and they have their own interpreter GIL, which means that they don't suffer from it, and they can truly run in parallel. And of course, you have multiprocessing that can run things in parallel, of course, because you have one dedicated process, but then you have the problem of serializing data and synchronizing data between your processes. So this is the typical web server architecture, at least in theory. You have a bunch of clients making requests through a network that are served by servers that can be replicated in several processes, but usually they access a single database in the backend. So that's the theory, and in practice, well, the database is kind of far away. There is a lot of latency, and as we know, latency is very bad for performances. So this actually, all the credits goes to Yuri Selivanov, who made a talk at PyCon US last year called Overcoming GIL with Subinterpreters and Immutability. So you can find the video on YouTube. There is a nice recap by Catherine Mitchells there. You can take a picture and check it out later. And this talk was actually accompanied with a library that Yuri wrote called Memhive. It's a proof of concept library. It's actually written in the README. Do not use in production or you will be fired. And actually it's not very developed, but there is one issue, which is mine. And because I was very interested in this kind of use case, and I was wondering if CRDTs could be used for this the same use case. Yuri actually used another algorithm in Memhive, which is called HAMT, for hash array map tree. This is based on immutable data structures, where every change creates a new branch in a tree, like a diff, a patch to the original data structure. The branches are referenced from the parent parent node, so it means there is no copy for reading, and you can actually have mutation on top of these immutable data structures, and it's actually implemented in a very efficient way. So Memhive takes advantage of HAMT and shared memory in subprocesses to reference data from one subinterpreter in another one. So there is no copy for reads. As I said, it's very cheap. You have the guarantee that data won't change under your feed, so you don't have to manage any lock. And there is efficient mutation because only the changes are copied back to the original data structure, which means only the diffs. So that's what we want. So these are some slides from his original presentation. This is the basic architecture. You have a main subinterpreter, dispatching work to some sub-interpreters, talking to them through queues, but it's not using pickling, it's using this HAMT algorithm with the shared library safely stored in the main subinterpreter. And that's basically how it works. So you have a parent map, for example, stored in the main subinterpreter, and when it's mutated in one of the subinterpreters, a new node is created, but it's just referenced from the parent node, so there is no copy of the whole structure. And then when the worker subinterpreter is done, maybe it added a new entry in the map, only this branch is copied back to the main subinterpreter, and it's very fast because it's just a mem copy, basically. So HAMT and memhive are probably great. The pros is that it's very fast, only the differences are exchanged, but the cons is that I didn't see any support for nested data structures. I could only see basic maps with keys and values, but nothing like maps of list, for example. It's only possible because of this possibility to share memory between subinterpreters, as far as I can tell. So it doesn't scale to distributed out-of-core architectures. And there is some hack in order to keep the original data structure alive in the main subinterpreter, because the garbage collector could potentially collect this data if it's not used by the main subinterpreter. And also, there is no conflict resolution, so workers are not notified of data changes, and they cannot react, for example, to changes made by other workers. So here comes CRDTs. CRDT stands for conflict-free replicated data type. It's a data structure that where each peer, let's call it them peer, each core, if you will, has their own copy of the data. And data is really local first. So it means you access them as you would access, for example, a Python dict, very fast, almost as if it were local, and changes occur in the background. So, and you can get notified about changes that can happen remotely by other workers. And the big feature, if not the main feature of CRDTs, is that conflicts are resolved automatically by this the inherent algorithm. In the Python ecosystem, we have PyCRDT, which is a Python binding to the wires Rust library, which is itself a port of the YJS library, JavaScript library, very famous, very popular. They deal with JSON-like data structures, so it's very convenient. It's like structures as we know them: maps, lists, integers, strings, and it makes no assumption about the transport mechanism that you can use to synchronize your data. So it could be HTTP, it could travel, not even travel, it could be stored in memory. It could be a client-server architecture. It could be a peer-to-peer architecture. It doesn't care. You can also see CRDTs as a distributed database where each worker has their own copy of the states, and states are allowed to diverge temporarily. Of course, in the end, what we want is eventual convergence. So we want that in the end, everybody works on the same data. But basically what we do is we trade strict data consistency for immediate access. We prefer to have access to the data immediately, even if it's temporarily not the data that everybody shares. So the pros is no latency at all, no lock to deal with. And the cons is that changes might conflict with other peers because they can do things at the same time. And synchronization might take time and CPU cycles. So this is a Yuri in his presentation used a very simple example to benchmark a little bit some performances when you have in the main sub-interpreter a map with 1 million key values and the worker mutating 100 of them. And I tried to replicate his plots. So basically, we start with a dictionary of 1 million keys. We pickle them, so we simulate some kind of transport. So yeah, first he was trying to compare brute force pickling with HAMT. So we pickle them, we unpickle them, we change them, and we again pickle them, unpickle them on the other side, and we measure the time it takes. Using CRDTs, you can see that the code is not that much complicated. We have special structures from PyCRDT, so a doc, which we call doc, which is a kind of root data structure from which we extract a map. We also initialized it with 1 million key values. We get the update of this doc, we transfer it to some kind of remote doc. We apply the updates, and then each change that we are going to do on this remote doc are going to be observed and applied back to the local doc. And if we plot that, we see that CRDTs are very fast compared to pickle. It's basically instant compared to pickling. So this graph shows the number of key changes, the time it takes to change a number of key values. In Yuri's presentation, it was basically the same. HAMT is in blue and unpickling is in green, but so we cannot really say much about this graph. We have to zoom in to the CRDT, for example, to see what's happening, and we see that the more key values we are mutating, the more it takes time to synchronize the two peers. And for HAMT, it was basically the same, but quicker. Here, for 100 values, it's like 1.4 milliseconds, and it was 0.2, so much quicker for HAMT. If we try on a much smaller data set with only 10 key values, here we can see that CRDTs are still, in this case, slower than pickle, while it was the opposite for HAMT. So that's also a win for HAMT. But all this is very theoretical because it actually depends on the architecture in which we are going to replicate the database. So, and one good thing about CRDTs, as I said, is that there is no assumption about the transport layer or the topology. So we could use any one of them. In a client-server architecture is typically a star topology. In a peer-to-peer, it could be a line, for example. So I've tested 3 architectures, 3 combinations of architecture and transport layer. One is a client-server architecture using HTTP, so it's the star topology. So here, each client has its own copy of the database talking to a server that has also the same database. client-server architecture using memory pipes to show that transport layer matters also, because memory pipes are much faster if you're working on the same machine. And peer-to-peer architecture using memory pipes. So that's the line topology that we saw before, where each client has their own copy of the database, and they are just connected to adjacent peers. And that's the typical results I got. So on the y-axis, you have the changes per second. We want that to be as high as possible. And on the right is, on the x-axis is the number of clients. So basically we see that HTTP is slow compared to pipe transport. We were expecting that. And we see also that, no, sorry, HTTP is slower than, pipe clients. And we saw also that, we can see also that client-server architecture is slower than peer-to-peer. And one thing which is kind of surprising is that it's slower with the number of clients. So that's not good. HTTP versus memory pipes, well, it's understandable. HTTP involves a network stack with TCP for reliable communication, IP for routing. If you don't need that, if you're on the same machine, obviously it's going to bring an overhead that you don't need, but also it allows you to go out of core and scale to remote machines. So it's a trade-off. Memory pipes are local, so they are much quicker to do inter-process communication. So it's the best if you're sure you're going to stay on the same machine. Comparison about client-server and peer-to-peer architecture. So as we saw, the number, the performances were decreasing with the number of peers, and that's because actually the server's load has a lot of burden because it has to relay all the updates to every client. The clients might be idle themselves. They could handle more traffic, but it's the server that is the bottleneck in this situation. And actually replicating the server doesn't really solve the issue, because in the end, if you're replicating the server, you still need some kind of other server that will synchronize all these sub-servers. So it doesn't really scale. And peer-to-peer is actually interesting in this situation because it can be seen, a peer in this situation, it can be seen as a small server where it's connected to one or two other clients, as we've seen in the line topology. But maybe two clients, but obviously not all clients, as in the star topology. So it certainly puts less load on every peer. So yeah, it's kind of a conceptually equivalent to server replication, but some peers have to act as pass-through for connecting all the other peers. So there is some something that is not optimal there. In conclusion, can we say that CRDTs scale for multiprocessing? It's not obvious. Local changes are done almost instantly because CRDTs are inherently local first. So we have very low latency. Synchronization can be slow, as we've seen with these different use cases. But on the other hand, it offers a lot of services, automatic conflict resolution, and it's done in the background. So actually, this is a good trade-off, I think, because it means that CRDTs can be used very efficiently can be actually a very good solution for peak load because you have high availability and almost no latency. And you can use idle CPU cycles for catching up with global changes. Here are some future directions to try to improve this situation. So exploring more peer-to-peer architectures. As we've seen, there is not only line topology. Maybe some optimizations in PyCRDT. Wires, which is the REST library, is fast. But what about the Python bindings? There is some layer here that adds some overhead, and maybe we could think about using Cython in critical paths. And I started this library called WireDB, in which I will try to explore building this kind of distributed database using CRDTs. And what I hope to show is that it's a very, very flexible way to implement a distributed database using any kind of transport or topology. So thank you for your attention.
Thank you very much, David. Now it's time for questions. Do we have some questions?
Hello. What kind of data types are available for in PyCRDT? Is it just JSON-like data types, so maps of stuff, or is there something else?
So yeah, you have the equivalent of a Python dict. We call it a map. The equivalent of a list, it's an array. The equivalent of a string is a text. You have kind of native types such as floats, ints, and immutable strings. You have also things that are more targeted to XML elements, but that's kind of esoteric. I don't use them personally, but it's used in certain scenarios where, for example, web development. But yeah, that's basically, and you can combine them, so you can have nested types, an array in a map, and so on.
And what kind of transport, where you said it's transport agnostic, but you have to have some kind of encoded to serialize it on the wire? Is it some kind of binary optimized protocol? Is it something?
So yeah, it's a binary protocol provided by wires. It's supposed to be very efficient. There are two versions, actually. We use only one of them. The other one is supposed to be maybe quicker in very specific situations, but so that could be also, yeah, one thing to try, but it's not a bullet. It's not the perfect solution. I'm sure it has drawbacks also.
I have one question. Sorry if I cut in one. In all of these examples, the data structures were in memory because you had to hold the entire document in the process memory for all of the workers. Is there any work towards handing off some of the, if it's a large data structure, only really loading the parts that you want to modify, and yeah.
Yeah. So first, you probably want to have all this structure in memory if this is the data you are working with. All the cores probably should be able to have the whole structure in memory, but it's true that there is an effort right now that to have some kind of equivalent wires, which is this REST library called Wiser. So it's kind of just inverting the letters. It's YSR, but it's also wiser in the sense that it doesn't load the whole data structure in memory, and it uses LMDB actually to do some kind of lazy loading and have a disk-based backend, an efficient way of storing them on disk and only have some parts of the data in memory.
I have another question. I don't know. I'm not quite sure you covered that partly when the sort of transport agnostic, feature, could be interesting if you want to use the best of both worlds. Like you have on one server, local workers communicate peer-to-peer, over pipes, and then for anything exogenous, it goes over WebSockets or whatnot. Like, is there something that?
Yeah, definitely. Yeah, that's part of the topology we could explore. I mean, anyway, when you're done scaling up on your machine, you can't handle more load. That's probably the thing you want to do, and it's very easy to do. That's what I want WireDB to make easier to do, actually. So yeah, kind of building this topology easily.
Did you try to plug this into something like Dask, which already has also communication protocol?
Yeah, I know that Dask does some peer-to-peer communication between the workers. I'm not sure if they have some centralized place for storing some kind of global state.
Yeah,
probably
the scheduler.
Okay. Probably we should talk to them to see if they could be interested in that. And also, it may make sense to use CRDTs in cases where workers may go down, for example, because it's kind of a more resilient approach, because every peer has a copy of the data. If one core goes down, the data is not lost.
Are there any more questions? No? Okay, I just have a question, but I'm no expert in this field. That's why I'm asking from my field, which is machine learning. Does machine learning have can it have some expectations from CRDT? Like, can it improve some parallelization for running machine learning models, especially the large LLMs? Well, LLMs are large, but like the big models, can it have some benefits? Or in any other field like mining or something? So which fields could be particularly benefited from this kind of CRDTs?
Yeah, I'm not sure it's really related to the field, but rather to the way they are deployed. For example, in ML workloads, they are probably deployed using some kind of shared database, and this is what CRDTs can replace.
That's great. Probably some good news coming in some time. Okay, so if we do not have any more questions, I guess I would first thank David for the amazing talk. And then actually this has been a short session, so this concludes the session before you go to the lightning talks actually. So let's applause David.
Thank you.